Okay, so welcome to Cinco de Mayo. Hopefully everybody's having a good day today. And today in DiffyQs, we're going to continue where we left off, which is looking at how do we solve now these non-homogeneous second order differential equations, right? And we walked through an example, just like a real simple one, where we had it, a differential equation equal to like x squared or something silly like that. But I want to formalize it a bit. I want to get into how do we attack these things in general? Because there are some patterns, there are some goals, and there are some techniques. And so we need to start getting into that. So that's my plan, to sort of pick up where we left off. But before I go there, any questions about the homework or anything else that we've been talking about?
So on Monday, I was having technical difficulties with my internet, and I just ended up leaving because I didn't want to keep popping in and out. I figured that would be distracting. So, do you mind just going over real quickly what the main concept was of Monday's lecture?
Uh, yeah, I'll kind of do that. I think when we kind of get rolling, I'll give you the recap.
Cool, thank you.
Yeah, for sure. And in the future, it's totally cool if you want to keep popping in and out. It doesn't actually distract me. I don't know if it distracts other people. It shouldn't. Um, but yeah, if you're having issues, feel free to try to hop in and out as much as you need. So, but yeah, hopefully I'll give you the little brief rundown, and I think you should be good with us going forward. Anything else? All right, well, hearing none and seeing none, we'll go ahead and pick up where we left off. So let's just sort of go to the recap of what we're trying to do now that we've got the non-homogeneous. So let me pull up a whiteboard here. I'm going to give my phone a rest, so we'll just do it this way. Okay, so what we started looking at is, suppose that we've got the non-homogeneous. And I'm not even going to go to necessarily constant coefficients yet, because most of this just totally applies regardless of what these functions are. All right, so we're going to have this. So y double prime plus p of x y prime plus q of x y equals f of x. And now f of x, of course, is not 0. So the first thing that's kind of big is, and I think I called this theorem number 1, was that we're guaranteed a unique solution when? What has to be true for us to have a unique solution here? Anyone remember? Okay, good, Ralph. So you just said the functions of x are all continuous. And that's true. What we need is P, Q, and F are all continuous. So we saw exactly the same thing for the first order. It's just there was no Q. And so we needed the P and the F to be continuous. Now we just have to throw on the one extra. Okay, so that's the first thing, just in general. If we're looking for a unique solution, these things have to be continuous. Obviously, we're talking about an initial value problem. They have to be continuous in an interval that contains whatever our initial condition is, right? Like if we were looking at, say, y of x naught equals y naught, is going to be there all in continuous in something that can in interval that contains x naught. All right, so that was kind of a big deal. We also saw, and this is actually probably the more important one, is that if we've got, say, y1 and y2 are a fundamental set of solutions to the homogeneous, So I'm going to put here corresponding homogeneous. Then what we know is that the solution to the non-homogeneous is of the form y equals yp plus c1y1 plus c2y2. And does anybody remember what yp is? What this actually represents? The P stands for particular, so it's particular solution. But what it is, YP, is any solution to the non-homogeneous. All right, so all we have to do is find one, any one, and that will be the YP. And then we can just add it to the solution set for the homogeneous. So this is really the extra step. You think about what we have to do to solve the homogeneous. We still have to find the Y1 and the Y2. It's just, this is the extra step. All right, so what we're going to be concentrating on anytime we're dealing with non-homogeneous is how do we find that Y particular? Because the other two, the Y1 and the Y2, we already know what we need to do to find them, or well, we're working on it, right? At least in the context of the linear second order with constant coefficients. Those we know, right? You make your polynomial, you find your roots, depending on what those roots are, you put it into the respective forms and go, right? But it's going to be that YP that we got to work on trying to find. So that's what we're going to talk about today. All right. So the one other thing I just want to remind you about before we dive into doing these other problems is when we have the linear second order homogeneous with constant coefficients, right? So these are the A y double prime plus by prime plus cy equals 0, where A, B, and C are just numbers. What we saw, the process there was we created the polynomial. So I make AR squared plus BR plus C equals 0, and we find the roots. And I just want to remind you that the three different cases lead to three different kinds of differential equations or solutions to the differential equation, right? So the first case is two unique roots. And in that case, y1 is e to the r1t, and y2 is e to the r2t. So we actually saw those like a week ago, or the very first ones we did, we saw an example of that. But those are the nice ones, right? When we get two unique roots. If we get a repeated root, okay, well, we still get the e to the r1t. Does anybody remember what the second one looks like?
T to the t.
There you go. Te to the r1t. So we just multiply it by t. When we did the very first example, just kind of trial by fire, we ran into that, but then we did it last time generically, and we saw that it has to be that we multiply by t, right? That guarantees that they're linearly independent and it still is a solution. All right, and then the third case was complex roots, right? And in this case, we're going to have r equals I think they used omega in this book. If not, I'm going with it. So these are the alpha plus or minus omega I, right? The complex numbers. And in that case, what ends up showing up are trig functions. So what we get for our solutions are y1 equals e to the alpha t cosine of omega t. And then y2 was e to the alpha t sine of omega t. So those came from Euler's formula, which was that nifty little trick using power series. And it's the one thing I'm going to bring up, Bradley, that you might have missed. I don't know if you saw that or not. But if you didn't, come chat with me sometime and we'll talk about Euler's formula because it's kind of an interesting derivation and a nice use of power series. All right. But
Yes, sounds good.
that's what leads to these two. So when we first did it and we first proposed what kind of functions might do this for us, we saw exponential functions were one of them and we saw trig functions were the other. And now you can see why. Now you can see why those are R forms in general with some slight variation on. So all of this, the bit that I have here about finding the solutions to the homogeneous, we're going to need because that's going to give us our y1 and y2. Right? So we have to do this part anyway. And then the next extra step is find that y particular. All right, so that's kind of where we got last time. And we just tried one. And what we did was we made a guess. Kind of in classic differential equations form, right? I mean, think about what we do. We do that all the time. We just go with the, well, let's try this. Maybe it'll work, right? And we saw that it did for that specific example where our non-homogeneous part was like x squared or x cubed or x, I don't remember, some polynomial. Okay, so let's kind of formalize that a bit. Let's actually talk about this process. All right, so let me go ahead and clear this. So I'm just going to call this defined YP. So we are going to have some different methods that we do this. And the first one is a method called Undetermined Coefficients. Sometimes you'll see that referenced as the UC method, right, for undetermined coefficients. So that's one method that we're going to use. And that's what we're going to talk about today specifically. I'm going to give you, let me just give you a couple more because it's weird to have a list that only has one on it. We're going to do another one that's called reduction of order. Guess what it does? It reduces the order of your differential equation. So it turns it from a second order to a first order that then we can solve. Ooh. So there's called reduction of order. And then a third one we're going to talk about is called variation of parameters. And there are more depending upon what this thing looks like. But these are the three that we're going to talk about. We're not going to get to all of them today by any stretch of the imagination. But they are the three big methods we're going to do. Okay, so let's start with undetermined coefficients. So we're going to look at this guy. And let me actually just translate this for you, because undetermined coefficients, if you read those words, it's pretty self-explanatory. Coefficients, so the numbers out front, are undetermined. meaning they are variables, right? But what this really means is we're going to guess a solution. So guess at the solution, I guess is how I want to say this. So this is a really fancy way of saying, well, I don't know what y particular is, but I know what it should look like. So let me guess this form. So this is definitely a pattern recognition kind of deal. All right, now our discussion is going to be centered around those with constant coefficients. So we're going to specifically look at these kind of differential equations. If we, if we change it so we don't have constant coefficients, the goal is still to find a particular solution and then to add that to the solutions that we get that form a fundamental set to the homogeneous. It's just we don't know how to do that part yet for other forms. So we we'll get there, but we're going to be looking at this kind of form. All right. Now, what's really going to drive our guess is the f of x. All right. And so what I'm going to do is I'm going to make a little chart here that has f of x in it. And then on the other side, we're going to talk about what kind of guess we want to make given what f of x looks like. All right, now, the first nice form is if f of x is a polynomial. And the example that I showed you last time was one of these. I mean, it was a simple polynomial. Like I said, it was x squared or x cubed. I don't really remember which. But what did we guess? What kind of form did we guess as a particular solution when our non-homogeneous part was a polynomial? Do you remember what we did last time? Or you can go back and look at it. No, nothing.
Is y of p a function?
Yes,
constant?
yp is a function. And it's a function that satisfies the differential equation.
Okay.
All right. So Ralph, I see you just put in ax squared plus bx plus f of x. You're definitely on the track of where I wanted to go. And if this thing is equal to a polynomial, we're going to guess a polynomial. Because if y is a polynomial, its derivative is a polynomial. Its second derivative is a polynomial. And so there's definitely a high likelihood that if we take all those polynomials and add them together, we get a resulting polynomial. And in terms of the degree, we're actually going to guess a polynomial of the same degree. So like if f of x is a quadratic, we will guess a random quadratic. If it's a cubic, we'll guess a general cubic, and so on. And if you think about it, it should make sense, right? Because let's say that f of x is degree 5. The only way I can get 5th degree pieces is if my y is 5th degree. Because y prime is going to be lower degree, y double prime is going to be lower degree. When you differentiate, you drop degree. So the highest degree is going to show up in y. All right, well, to ensure that we've got the same degree as our f of x, that's what we're going to guess. All right, so let me show you what I mean. Let's do an example here that's a little bit more complicated, or at least, well, complicated looking. I don't know if it'll end up being more complicated, but a little more complicated looking than the one we did last time. All right, so for example, let's say we've got 2y double prime plus 5y prime minus 3y equals 4x squared minus 2x plus 1. So this is a linear second order non-homogeneous with constant coefficients. All right, so we need to do this in 2 stages, really. The first is solve the corresponding homogeneous. So let me write that over here. We'll put the homogeneous up. We're going to have 2y double prime plus 5y prime minus 3y equals 0. So as we saw before, the trick here is to create the polynomial. So we're going to have 2r squared plus 5r minus 3 equals 0. And we need to find the solutions to this. I was nice. I gave us one that factors. It's 2r minus 1 times r plus 3. So that gives us r equals 1/2 and r equals minus 3. So then we know our fundamental set. Y1 is going to be e to the 1/2 t. And y2 is going to be e to the minus 3t. So always start there. Regardless of what method we're choosing to try to find the y particular, you always need to know the fundamental set to the homogeneous. So you might as well find that first. Okay, so before I move on, are we good at this point? Any questions so far? All right, so now we're going to go try and find yp. But like I said, we're going to make a guess. We're going to make a total guess for yp. So how about we go with, this is our guess. Since we've got a polynomial, I'm going to go with a generic polynomial of exactly the same degree. So f of x is a quadratic. I'm going to guess a quadratic. All right, so that's what I'm saying. We're going to guess at a solution. I want this. Well, we're going to figure out what a, b, and c have to be by using the differential equation. So let's get yp particular, or yp prime. So that'll be 2ax plus b. And then we need yp double prime, which is going to be 2a. All right, so if this is the form for y particular, these are the forms for the derivatives, which means when I plug them in, I need to get truth. So let's take these and fire them back in to their respective places. So we're going to get 2 times 2a plus 5 times 2ax plus b. Oh, not plus, minus 3 times ax squared plus bx plus c. And that's going to need to equal 4x squared minus 2x plus 1. Right? If this is a solution differential equation, when I plug it in, I have to get the answer. Now, what this is going to do is just give us a system of equations. So like, let's just distribute group-like terms and all that good stuff, right? So I'm going to get, in terms of the constants, I'm going to get 4a plus 5b minus 3c. Those are all the constant parts. The parts on a, or sorry, on x, I'm going to get 10a minus 3b. Lots times x. And then the x squareds, I'm going to get minus 3a times x squared. And again, that has to equal 4x squared minus 2x plus 1. And now I can just equate the coefficients. So I'm going to get 4a plus 5b minus 3c is equal to 1. We're going to have 10a minus 3b has to equal -2. And minus 3a has to equal 1. But this system we can solve. It's pretty quick from this guy that we get a equals minus 1/3. So then when we go and we get our b, if we plug that in, we're going to get minus 10/3 minus 3b equals -2. So we'll add our 10/3 over. That gives us 4/3. We divide by -3, it gives us -4/9. At least I'm hoping that that's what that gives us. I think so. All right, and then when we go to the last one, we're gonna have 4a, so -4/3, plus 5b, so -29, minus 3c equals 1. And similarly, we're gonna be able to solve for c. So let's see, that's gonna be -12 minus 32/9. So 41/9. I think that's -41/27. Again, I'm not entirely certain, but it feels right. All right, so we now know what YP looks like. Remember, we guessed this form. We can put these numbers in now. So YP is going to equal minus 1/3 x squared minus 4/9 x minus 41/27. So there is a function that satisfies that differential equation. It is not the only function, for sure, but it is a function that is a solution to the homogeneous. And that's all we need. Y particular just needs to be any one of them. Okay, so before I wrap this up, any questions on how I found that YP?
I have a quick question.
Sure.
You know how you said that's not the only solution for YP, but it doesn't really matter because we found one?
Yep.
Now, in an applied setting, are you going to want to be specific? Or
So
does it still not matter?
Okay, so it still doesn't matter in the finding of the YP. All right, because again, we just need to have any function whatsoever. I'll address the applied specificity in just a second. But in terms of finding YP, no, you just got to make sure you found a function, whatever it happens to be. Okay, so let's put this all together then to get the general solution to our differential equation. All right, so this is when we need the drum roll because we're at it. So here's what y is going to look like. It's going to have that y particular, but then we have to run back up here to where we had our fundamental set. And we need to put those in as well, but they get our coefficients. So we're going to have C1 e to the 1/2 t plus C2 e to the -3t. And so that we'll put a box around because that now holds every solution to this differential equation. And that was the key to that second theorem. That's why that second theorem is so important. because it says you can actually get all solutions by doing this. Let me tie it back. So let me first answer Bradley's question about, an applied setting, the specificity. All right. In that situation, if you're using this to build a bridge or whatever, you're going to have some initial conditions. And those initial conditions are going to determine the C values. They're going to determine these guys. And when I said this is just one solution, it is. It's the solution when C1 and C2 are both 0. Or, so that is that solution. But C1 and C2 can take on all kinds of different values, right? I mean, an infinite number of values for each one. So that's why I'm saying there are lots of solutions. We just happened to find one of them that worked. We could have found another one that was true when, we could have had this plus e to the minus 3t. That would still be one of the solutions, and we could have used that as our yp. It just that e to the minus 3t didn't jump out at us because of the form, right? Like the 4x squared minus 2x plus 1, that didn't suggest anything exponential to me, which is why I went with, well, let's just go with generic polynomial. And it works out because I just need a solution. Doesn't matter which one. All right, so when it comes to an applied and we're doing specific, yeah, you will find your specific solution given your initial condition. And that first theorem that I put up there says we're guaranteed a unique solution for an initial value problem, because that will specify the C1 and C2s. And it could turn out that we get exactly the same thing that we started with, is Y particular. That might be the solution to our initial value problem. It's unlikely, right? I mean, in essence, 0 probability, 1 out of an infinite number of options. But that can come up. So hopefully I kind of answered your question there, Bradley.
Yeah, you did.
Okay, cool. All right. So I know this isn't glamorous, and I know that you're begging for some sort of magic, here's how you do it. No, this is purely, we guess a form and we see what values that form has to take on for it to work. So it's not glamorous whatsoever, but it works. And all this is ever going to do is give you a system of equations. Right? You're going to have a whole bunch of unknowns. How many? Well, it depends on what f of x is and what we guessed, right? Like in this case, because it was a quadratic, we had 3 unknowns. But you can imagine if it was like a 10th degree, and then we go with a 10th degree generic, that's going to have 11 unknowns. So you're going to lead to an 11 by 11 system. So, I mean, they can get big, they can get ugly, they can get huge, but it will always ever lead to a, all you'll ever have to do is solve a system with these. Let me bring it back to linear algebra a little bit. Do you remember seeing structure like this in linear algebra? Where you have your basis is, your linear combination of all those forms of space, but then you add on something else that's not necessarily in that space? That's a real question. I don't know if Larry showed you examples like that or talked about that.
It sounds really familiar because I was literally just thinking this is just linear algebra.
Yeah. What it is, like a really good example, like if we're talking about like 2-dimensional vectors, and you'll have 2-dimensional vectors, whenever you have a 2-dimensional vector space, it always goes through the origin. So like if you had a plane, let's say, that cuts through the origin, that's a 2-dimensional vector space. But if you take that plane and you shift it up, shift it over, you shift it so it doesn't pass through the origin, it actually takes on, sorry about that, it takes on this kind of form where like these two pieces are forming the plane And then the y particular is moving it so that it's going through the point that you're interested in. And this is exactly analogous. The fundamental set is creating the space for the homogeneous. But when it becomes non-homogeneous, we just have to shift it so that it's going through the right place. Well, that's what we did. We shifted it using this y particular so that it now goes through 4x squared minus 2x plus 1. So I wanted to tie it back to that just in case you guys had talked about it. But hopefully you're kind of seeing the idea there, is that when it's homogeneous, we're forced to go through the origin. We're forced to go through y equals 0 because y equals 0 is a solution. Non-homogeneous, well, you just take that went through the origin and you shift it. All right, well, anyway, so I'm not going to do another example with a polynomial because I think you guys see what we need to do. It's not glamorous, it's not exciting. You just make your generic polynomial of that degree, take derivatives, fire it in there, create your system. All right, so let's change our type of function. Let's say that f of x is exponential. So I'm actually just going to reuse this, at least the non-homogeneous part, or the homogeneous part, I mean. And I'm going to change this so that instead of it equaling that polynomial, let's just make it equal, say, e to the t. Whoa, whoops. Sorry about that, guys. Press the wrong button. Okay, so we're just going to change that a little bit. Now, in terms of the solution set, we're going to do the same thing. We're going to have to go and find our solution to the homogeneous part. That's why I wanted to just keep that the same, because we already have all that work over here. But what we are going to change is our guess, because it clearly isn't going to be a polynomial anymore. Since polynomials, their derivatives are polynomials, you never get something exponential. So what would you think would be a good guess now for a form?
Something exponential.
I think that that's a really good guess because, yeah, exponentials, when you differentiate exponentials, you get more exponentials. All right, well, if we're going to go with exponentials, specifically, what exponential do you think we want here?
E to the t.
Okay, we're going to want the exponential that is exactly the same type here. So we are going to guess, for our guess now, let's go with yp equals a e to the t. So then the derivative is a e to the t. The second derivative is a e to the t. So when we put all that stuff in, we're going to get 2 times a e to the t plus 5 times a e to the t minus 3 times a e to the t, and we want that to equal e to the t. So combining everything, 2 plus 5 is 7, minus 3 is 4. So we get 4a e to the t equals e to the t. So a is 1/4. So from that one, then we're going to see, we see that 1/4 e to the t is a solution to this differential equation. When you go and you put it in here, you actually get truth. All right, which means that when we come in, we write what our answer is, the general solution to this differential equation. This is going to be 1/4 e to the t plus c1 e to the 1/2 t plus c2 e to the minus 3t. So if you look at this one and you compare it to the one we just did, the answer looks very similar in terms of structure. It still has the two fundamental set pieces. And then we're adding to it now a different particular solution because it's a different differential equation. All right, so with exponentials, it's pretty damn clear what we want to use. Our guess for yp is going to be the same exponential. Right? Like if this had been, let's say, e to the 4t, we would have guessed yp equals a e to the 4t. Now, obviously, that would have changed things because as we differentiate, that would have given us 4a to the 4t and then 16 ae to the 4t. And so put those in, you'll get a different a. But it's exactly the same idea. All right, so exponentials are beautiful. Super easy, right? Except. Let me change this. We're actually, I'm going to kind of change it significantly now. So let me just erase this real quick. Actually, before I erase it, you cool with this one? Did you like this one? Are you thinking, man, if they can all be this easy, then life is going to be good?
Yeah, but they won't.
Right. They obviously won't. But in this situation, yeah, that was pretty awesome. Okay, so I'm going to change it significantly and such that even our particular solution is going to change. All right, so let's go with this one as an example. Let's say we've got y double prime minus 3y prime plus 2y equals, and let's go with 4 e to the 2t. So I know it doesn't really look like much has changed here. Still the same kind of form, it's still exponential. Yeah, I put a 4 out front, but whatever. That just means that whatever a we find, we just multiply by 4. Okay, so but let's go through the steps. So we're going to start by finding the solutions to the. Well, I'll tell you what. Let's do the guess. Let's do our guess first. All right. So what's your guess for the form?
Exponential again.
Okay, so we're going to go with a e to the 2t. Right? We want it to be the exactly same kind of exponential, e to 2t, and we'll just choose an a. So y prime is going to be 2a e to the 2t. Y double prime is going to equal 4a e to the 2t. So let's put those in. So we're going to get 4a e to the 2t minus 3 times 2a e to the 2t plus 2a e to the 2t. Right? We need that to equal 4 e to the 2t. So let's see. So we got 4 minus 6 plus 2. Wait a minute. Wait. 4 minus 6 is negative 2 plus 2. Uh-oh. Like, this is a major uh-oh. Because not only did the a's go away, so I can't figure out what a is, but also I got a statement that can never be true anyway. Ah, shit. All right. So what happened here?
My guess is it's not linear, right? Is that the problem?
No, it's definitely linear. That, remember, you don't worry about the t parts, but just the y itself. So
Oh yeah, okay.
that part's linear.
Mhm.
It still has constant coefficients at second order. Like, I mean, this is still exactly the same in terms of classification. Okay, well, check this out. Let's go find y1 and y2. So we create our polynomial, which is going to be r squared minus 3r plus 2 equals 0. Right, just taking those coefficients. This one factors to r minus 2, r minus 1. So our two functions are e to the 2t and e to the t. All right, so do you see what the issue is now?
Y, our guess for yp is the same as y of 1, pretty much.
Yeah, it's a constant multiple of y1, which means it can't be a solution to the non-homogeneous because it's a solution to the homogeneous. That's why we got 0 here.
So in linear
Because it's
algebra
part of it.
world, it's linearly dependent.
So yeah, so this y particular is linearly dependent to y1. It's in the vector space spanned by y1 and y2. So it's kind of like it's in the null space. Remember the null space? It's the set of things that gives you 0. The guess that we made is in the null space. Well, that doesn't help us if we're trying to get something that's not in the null space. Okay, so all of a sudden, not so easy. All right, so what do we do?
I'm thinking maybe slap on a t,
Oh,
like chain rule or a product
okay.
rule sort of thing.
Okay. I like how you're thinking. Yeah, because if we had, say, if this was instead t e to the 2t, when you differentiate, yeah, you're still going to get t e to the 2t's, but you're also going to get, that's what we get, 2t e to the 2t. And then the other one, the other piece is going to be a plus e to the 2t, right? So like if y particular was this, yp prime equals this. So I like where you're going with that, Bradley, because for sure with the product rule, you're still going to get things of this form. You're going to get things that are not of that form, but they could potentially cancel out with the adding and the subtracting and all that because they keep showing up. So that's a good guess. I like that. That wasn't what I was thinking you guys might answer. Because what have we always done in differential equations when we're like, okay, I've got a form, but it's not quite the form I want?
We did an integrating factor.
Yeah, we go with the let's slap on an integrating factor. So let's see what happens if we do that. Okay, so I'm gonna erase all this because that guess of YP did not work. Bradley, yours might work. That's not why I'm erasing it, not because it doesn't work, but I definitely like where you were thinking there. But instead, let's try this. Let's go with, all right, we're gonna guess a YP that is U times e to the 2t. And there's going to be an a on there as well. But I'm not going to put it right there just to confuse. We'll put it on at the end. Okay. But let's just say we go with y equals this. So then y prime is going to be u prime e to the 2t plus 2u e to the 2t. Y double prime is going to be u double prime e to the 2t plus 4u prime e to the 2t plus 4u e to the 2t. This middle has pieces of both product rules. They both lead to a u prime e to the 2t. Each of them has a coefficient of 2, so I just add them up. All right, so let's see what that forces to have happen when we plug in here. So we're going to get u double prime e to the 2t plus 4u prime e to the 2t plus 4u e to the 2t minus 3 of the y prime. So minus 3, let me stack them up here. Minus 3 u prime e to the 2t minus 6 u e to the 2t. And then we're going to add 2 of the y's, so plus 2 u e to the 2t. All right, so all of this cancels. And what we're left with is u double prime plus 4u prime times e to the 2t has to equal 4 e to the 2t. And notice what happened was we actually have changed this so that it's no longer second order. I know it looks like it, but if we did a substitution, say w equals u prime, then w prime equals u double prime, and we've got w prime plus 4w equals 4. All right, so what happened to the minus 3u prime? Oh no, that was not supposed to get removed. Thank you for catching that, Ralph. Man, you've been on it, Ralph. I appreciate that. It should just be plus u prime. It was 4 minus 3. Thank you about that. Which then removes that 4 here. But in terms of what I was saying, that hasn't changed. It still gives us a differential equation that's just first order. All right, so we can go ahead now and solve that for w. Then we're going to integrate that to get u. And then we're going to take that u and multiply it by the e to the 2t. All right, so hopefully you see where this is going, but I want to just kind of cut to the chase because we've done a million of these. I know you're tired of them. You're bored to death. So let's just go, okay, that's what we do. But what does that turn out to mean? That, yeah, our guess is going to be t times e to the 2t. So Bradley, you are exactly right. I just couldn't tell you that right away. But yeah, that's the trick. All right, so why did this show up? Or why did we have to do this? It was because the guess, the form for the guess, showed up in our solution to the homogeneous. And when that happens, multiply by t. You might actually have to multiply by t squared or t cubed or t to the fourth. I'll explain how you can tell when that happens. But for us at this stage, we just have to multiply by t. So let's follow this through and let's see what that forces for our a. Okay, so y prime is going to be a times e to the 2t plus 2t e to the 2t. Y double prime is going to be a times e to the 2t plus 4t e to the 2t plus another 2e to the 2t. Right, product rule on that guy. So then when we put it into the differential equation, let's group it by pieces, parts. So we're going to have a e to the 2t. Actually, there's 2 plus 1, so there's 3 of them. So 3a e to the 2t plus 4a t e to the 2t. We're going to subtract 3 of these. So minus 3a e to the 2t. And then minus 6 a t e to the 2t. Oh, I did something wrong. Shoot. Okay, well, anyway, to backtrack and see what I did wrong. 2at e to the 2t. You guys see what my issue is? You see why why I said I did something wrong? Look at what happens when I add all that stuff up. What do I get?
0.
Yeah, and it can't be 0 because I know t e to the 2t is not in this set. What did I do wrong? Derivative t is 1, so derivative e to 2t is 2, 2t e to 2t. That derivative is e to 2t. 2, so 4 t e to 2t, 2 e to 2t. 3. Oh, no, that's no, never mind. 3a, 4a, minus 3a. I haven't for the life of me where I made the mistake.
I don't see it either.
Crap. Man, this is gonna gnaw at me. Because I can promise you this. The first line should just be y prime. So oh yeah. Cool. Ralph. Man, do you mind coming to all my classes? Because you've been catching everything for me. Man. MVP of this class right here. There you go. So a e to the 2t, not 3a. Thank you. Okay, now I feel so much better. Okay, so now when I add all that up, I get minus 2a e to the 2t plus 0. And that has to equal 4 e to the 2t. So I get minus 2a equals 4, or a equals minus 2. So that tells me that a function that is a solution to this is minus 2t e to the 2t. So then I can write out my entire solution, which is that particular, plus the fundamental set. All right, so this happens. And this actually happens a lot if you think about it. Like, what kind of forms are going to lead to this where our guess might be part of the actual solution set? Well, anything that came from the solution set. So exponentials, sine and cosine, right? So we have to watch for this. And when the suggested form, right, like over here where I'm making my chart and I've got my guesses, if our guess is such that in that guess, I've got fundamental set, we're going to have to multiply by t's. So I'll come back to that in a second. We'll formalize that a bit so you know when to multiply by t and how many t's and all that. But I want to add in one more form here. And that's if we've got sine and or cosine. And obviously you can just imagine for this, if y is, if we've got a sine or a cosine, we want y to be made up of sine or cosine. But what we're going to want is actually a combination of them. So even if just sine shows up or just cosine shows up, you still want to make a guess that has both of them. And that should totally make sense, because when we differentiate, sine leads to cosine leads to sine, cosine leads to sine leads to cosine, like they get all mixed up. So we need to allow for those possibilities as well. So let me show you. We'll use this same differential equation. We'll just change the non-homogeneous part. So instead, let's just make this equal cosine of t. And let's see what that does for us. All right, so we already know that the homogeneous solutions have exponential pieces, and that is not cosine. So we don't have to worry about a sine or cosine guess being part of the fundamental set. So that means we can just jump to the, let's make our guess. So we're going to go with y equals a cosine t plus b sine t. So then y prime is minus a sine plus b cosine. So then y double prime is minus a cosine minus b sine. All right, so we put that into our differential equation. I'm going to group them by sines and cosines. So I've got minus a cosine t minus b sine t. That's our y double prime. Minus 3y prime, so plus 3a sine minus 3b cosine, plus 2 times our original function, so that's plus 2a cosine plus 2b sine. So when we combine that all together, we get a minus 3b times cosine of t. These guys give us 3a plus b times sine of t. And now if we look at what form we wanted just cosine. That tells us a minus 3b has to equal 1. And 3a plus b has to equal 0. All right, so solving that system, it's actually not terrible. You get a equals 1/10 and b equals minus 3/10. So that means our particular solution is going to be 1/10 cosine minus 3/10 sine. So the solution to the differential equation, the general solution, is this particular plus the C1 e to the 2 e to the 2t, C2 e to the t. But again, we just made a generic guess. It led to a system of equations, but then we got a particular solution, and we were able to combine that with our homogeneous to get our answer. And if there was ever a day to really highlight the why this is monkey math to me, today is that day. Right? Like, think about it. Are we even really thinking at all now? No. We're just going through the motions. And it's the same thing every time. It just changes because now we got a cosine instead of an e, right? But it's very procedural, which is awesome for people that like that. I'm not one of those people. It bores me. But there are people that like well, here's the process, just do the process. If you're that kind of person, you're going to love this. If you're not that kind of person like me, it gets old fast. Okay, but let's kind of formalize the multiply by t business. Because it probably even freaked you out a little bit that I said, yeah, sometimes you have to multiply by t squared. And sometimes you have to multiply by t cubed and. Okay, so I'm going to go ahead and clear all this, but let me real quick just double check. Is everybody good with the process here? What we did? Any questions? Ralph, did you see any mistakes I made? All right, looks like we're good. So let me go ahead and clear this all out. All right, so let's get back to the what about the t's, right? So when do we multiply by t? What about t squared, t cubed, and so on? Okay, so obviously when it happens, right, we need to do it when the fundamental set has the same form as f of t or f of x. Okay, whatever we want to call it. All right, so we're going to multiply that form by t to the s. And I apologize that it's an s, because I know my s's look like my 5 sometimes. This is the standard. So you'll see this in any textbook. But we're going to multiply by t to the s. And what s is, this is the number of times that, how about say the number of times that the root that leads to that piece of the fundamental set appears as a solution to the characteristic polynomial. So if it shows up just the one time, kind of like we saw with that example with e to the 2t, since it only showed up one time as a root, we multiplied by t. But where I'm going with this and why I wanted to show this to you is that later, not too long from now, we're going to go to higher order differential equations. And you're going to see that the process for higher order is the same. If we've got constant coefficients, but it's like fourth order, fifth order, you create that polynomial. It's going to have more roots, which is going to allow for more repetition, which could then allow for needing a higher power of t. The other word we use for this, by the way, I don't know if anybody remembers this from pre-calc, but this whole, the number of times that the root shows up, we call that the multiplicity. So I don't know if you remember that term, but the multiplicity of a root. If you do, that's the same thing. If you don't worry about it. But when we go to higher order, we get larger polynomials, which increases the likelihood that we have multiplicity more than one. And that will lead to needing higher powers of t. But even what we've been talking about leads to that possibility, right? Like, what if, let's look at this guy. Let's say we've got y double prime plus 2y prime plus y equals 2e to the minus t. So the very first thing you should do with any of these problems is immediately go to the homogeneous. Because the homogeneous, A, you need to do it. But then B, we need to be able to check and see if it shows up in our guess. So this guy would be r plus 1 quantity squared equals 0, which gives us e to the minus t. Right? So that's y1. Now we already saw, because it shows up again, we need a t e to the minus t. And if you come back and you look at this, and you'll see, okay, I need something, an e to the minus t. Oh no, that showed up in my fundamental set. Oh no, it shows up twice in my fundamental set. That means that my guess needs to be a t squared e to the minus t. And hopefully you see why it has to be a t squared. Right? What would have happened if I had just guessed t times e to the minus t?
We would have gotten linear combinations of both of them, or
Yeah.
linearly dependent sets of both of them.
Yeah, you come back to this and you go, well, crap, it's already in that. That's going to lead to the 0 as well. And it's just part of the fundamental set anyway. All right, so even in our situation, there are times we have to multiply by t squared, but this is the only time that you have to do it. The only time you're going to have to do that in the second order case, this linear second order with constant coefficients, is when you get the repeated root. Okay, because that's the only time we get multiplicity more than one. But once we're here, okay, well, we do exactly what we've always done, y prime. Well, that's 2at e to the minus t plus minus got ahead of myself here, minus at squared e to the minus t. And then y double prime is going to be 2a e to the minus t minus 2at e to the minus t minus 2at e to the minus t plus at squared e to the minus t. When I combine all that stuff together into this form, y double prime is going to give me 2a e to the minus t minus 4at e to the minus t plus at squared e to the minus t. I'm going to add two of these, so plus 4at e to the minus t minus 2at squared. And then we add in our original function. So cancel, cancel. So I need 2a e to the minus t to equal 2e to the minus t, which gives me a equal 1. So I got my particular solution. Putting it all together gives me y equals t squared e to the minus t. That's a particular solution to this. Plus my other pieces. So exactly the same process. We just have to throw in that t squared. All right, so that's how you know when it has to happen, is when your particular solution or the guess that you're going to have for your particular solution has the same form as part of the fundamental set. Okay, so it's pretty easy to recognize when you have to do that. All right. So we have those three basic forms: polynomials, guess polynomials, same degree. Exponential, guess same kind of exponential. Trig function, sine or cosine, guess combination of sine and cosine. But there are a couple of other forms that we can have that lead to also good guesses when they're combinations of these things. All right, so let me show you what I mean here. So I guess I'm going to add to our chart of the form of f and what we should guess. Hold on, I need that further over. Okay, so what if we have a polynomial times an exponential?
We're gonna guess a polynomial times an exponential.
There you go. You're going to go with the same kind of exponential and the same degree of polynomial. Because again, think about chain rule. Like if we kind of approach this like Bradley at the very beginning when I was like, oh, what do we do? And he's like, multiply by t because chain rule or product rule is going to give that to us. Same kind of deal here. Similarly, if you have a polynomial times one of the trig, take a polynomial of the same degree. Times a trig combination. All right, what do you think we do if we have exponential times a trig? Yeah, I think you're starting to see how this plays out. We're going to guess the exponential times the trig because the same deal, product rule is going to give us those potential forms. And then the last one is what if we have a polynomial times an exponential times a trig. Yeah, okay, well, you're going to do a polynomial times the exponential times the combination of the trig. So even when you have variations on this that are made up of the different pieces, you just make your guesses as products of these things because of how product rule works. Excuse me. But you can just imagine now how big and horrible these guesses can be. Right? Like, for example, let me just, we are not going to find what all the different parts are to this, because I definitely don't want to do that. I know you don't want to do it. But let's do this. Let's say, here's our differential equation. Okay, so we're just going to go with y double prime minus 2y prime plus y equals. And let's say we've got 3t squared e to the t sine of t. All right, so this is the horrible, it's all three of them. All right, so let's start building our particular guess. So we need a polynomial of the same degree. So that's going to be an at squared plus bt plus c. Okay. But then we need to have our e to the t. And we could slap another letter on there, but it's not necessary because that, whatever that number is, could get multiplied through, right? But then we need to have a d cosine of t plus e sine of t.
Order with those doesn't matter because it's commutative, right?
Whether I write cosine sine or sine cosine?
Yeah.
Yeah, no, that doesn't matter. Okay, so this is what the form suggests. But remember, we always have to go back and look at the homogeneous and see what that does for us. This one, the homogeneous, r squared minus 2r plus 1. That gives us r minus 1 squared, which tells us e to the t is part of our solution set. And then also t e to the t. All right, so are these in our form?
Yes, because our y of p has a t squared, so that doesn't ruin it for us.
Okay. So it turns out that these actually are not part of it. I know it looks like it because you go, oh, there's our e to the t, there's our t e to the t, but they're also being multiplied by cosine and sine. So the actual pieces of this, like if you were to distribute it all out, there's never just an e to the t. There's an e to the t cosine of t and an e to the t sine t. So we're actually okay for this one. But where it really could have been an issue is if we had gotten the complex roots that lead to this kind of form. So luckily we don't have to do anything else, but just as it is, check it out. We've got 1, 2, 3, 4, 5 different unknowns. And where this could get really crazy is, well, what if we had this 3t squared e to the t sine t, but then we added on to it a t cubed e to the t. So that's a whole nother structure, which is going to suggest, okay, I got polynomial times e. So I need a, oh, I can't use a. Hold on, I already used a. Where are we? Oh, we're on f. Okay. So this is going to be f t cubed plus gt squared plus ht plus I times e to the t. So we have to get 4 more just from this piece. But now this piece, we do run into the problem of the e to the t and the t e to the t showed up twice. So we got to multiply that by t squared. Okay, so this one, if this was what we were solving, we're actually up to 9 unknowns. Okay, well, let's just, for the hell of it, we won't put another horrible thing on there. We'll just put another cosine of 2t. All right, well, that means we also need to add on a, where am I? So j cosine of 2t plus k sine of 2t. And now we have 11 unknowns. Well, obviously, I mean, this can get as big and as ugly as we allow that non-homogeneous form to be. But at the end of the day, we're just making a guess. We're looking at that form and going, all right, to get that form, I need a polynomial times e to the t. Oh, I need a sine and cosine. I need whatever. But we always have to double check it against the solutions to the homogeneous, because those parts are not going to be any benefit to us. They're going to disappear. And because they disappear, we have to multiply by the t's to make sure that they stick around. All right. So if you are not the kind, if you're the kind of person who does not like algebra, you are going to very much dislike this stuff, because it's all algebra. Once we set the form, and then, yeah, we take some derivatives. After that, it's all algebra, and it's really easy to make mistakes, as I've tried to, intentionally show you. Yeah. No, it's really easy to make those mistakes and then be like, what the hell? Why did everything cancel out? They shouldn't have. So my strong suggestions here are go slow. Go slow. Start with homogeneous. Okay, start with homogeneous. Then go to your guess and check your guess form against homogeneous. Because once you get your guess form set up, like now that I've got this, I got my YP equals. Now I can turn on cruise control. Now it becomes monkey math. Now it becomes take derivatives, plug them into the original, set up your system of equations, find your, in this case, A through K. All right, so slow and steady, slow and steady, slow and steady. All right, so any questions on the setup of this one? How I built what I was using?
I have a quick question.
Sure.
Almost all of these are product rules. What if we have, function composition and require chain rule?
Okay. So, and I'm actually kind of glad you asked that, because you're right. Like everything I've shown you so far with this undetermined coefficient, I mean, it's really 3 things, right? It's polynomials, exponentials, and when I say trig, I mean sine and cosine, or combinations thereof, right? Mixed together. But what about other stuff? What if we don't have those? right? And I think you're hitting a good one, Bradley, where it's like, what if we've got some kind of composition? Or even without composition, what if we just have something as simple as natural log, right? Or anything else that's some sort of, or sine x over x or anything like that. Well, that's why we have other techniques. Really, undetermined coefficients only works well when you can guess a form that is going to be the only thing that can lead to your non-homogeneous piece, right? Like if you, at the end of the day, if all you have is a sine in your non-homogeneous, that came from sines and cosines. Those are the only things that are going to differentiate and give us sines and cosines so that we can combine them and get what we need, with the exception of multiplying by t's or something like that because of product rule. So when we're not in that situation, where that f is uglier, gnarlier, we got to try other things. And that's what the other techniques are going to do. So I guess the answer to that one, Bradley, is wait for it.
Sounds good.
Yeah. But I appreciate the question for sure, because that's kind of an important piece here is you don't always get things that you can guess the form on. So. All right. Any other questions at this point? Okay, well then we're going to go ahead and call it. I don't think I have anything to remind you about because homework's not due for a while. The next set of homeworks aren't due for a while. So I guess I'll just say, hey, have an awesome couple of days. Get out there and enjoy the weather. Man, it is a beautiful day out there today. Hopefully we get the same for the next few days. But other than that, I hope you guys have an awesome couple of days, and I will see you all next time.